Hello, everybody on Zoom in the lecture hall from the future. I hope you had a good Easter break. Good Zarsilut. Today, we are going to continue what we started right before the break, namely data modeling. I already showed you that XML and JSON are trees. These are models based on trees, where more exactly, these are syntaxes. And the underlying data model is based on trees. So normally, you should be able, if I give you any JSON document, you should be able to draw me a tree. That is the corresponding structure. Who can do that? Okay, I have a majority. Very good. The same with XML. If I show you an XML document, you can draw a tree as well. So the JSON tree is implicit because it's actually so simple that there is not a specification that tells you, it's just natural. For XML, there is a specification that tells you how to draw the tree. It's called XML info set. It's actually quite complex, but I simplified it for you with just elements, attributes, text, and documents to keep things simple. All right. So that was the part where what's going on. We have data stored in documents, in text files. Maybe you downloaded them from the internet, or you got them on a USB stick or whatever, right? So you got these are text files, and you need to query them. You need to extract the data and query the information. Well, we will see very shortly how we can actually query the data, but there are a few preparation steps required before that. We need first to open these files and create the trees in memory. Why? Because it's actually much faster to work with the trees in memories than it is to directly work with the text. Right? So this is the main reason. So what's going on is that when you open a file with MapReduce, with Spark, with an editor, with whatever, with Oxygen, the first thing it's going to do is convert that text to a tree. And the tree, the edges of the trees, these are all pointers in memory, right? You have this actual structure in the computer memory. All right. And the next thing you do, so once you have checked that and you are able to parse to a tree if it is well-formed, if it's not well-formed, you will not be able to create the tree, right? It has to be well-formed for you to be able to create the tree, well-formed JSON or well-formed XML. I use the word parse. This is called parsing. You parse an XML or JSON document, you parse it to the memory structure, to the tree, like this. Okay. And once you parsed it and you have the tree in memory, then you can ask another question. You can ask, is my document valid or not against a specific schema? And now we are going to see how we define these schemas that allow you to test for validation. But there is more work than well-formedness in order to do that. All right. So everything we're going to do in the next hour is basically that part on the right, where we are going to look at the question, is it valid or not valid, right? And I insist, I will keep insisting on that, do not confuse well-formedness and validity. Well-formedness is simple. Is it correct JSON or correct XML, and can you draw a tree out of it? That's well-formedness. And then you have the validation against the schema. And that depends on the schema, of course. So typically, when you download a data set, you might not have a schema. Sometimes they are kind enough to provide you with a schema, but sometimes they don't, right? So if you see a document like that, just to give you an intuition, a document like that, it's tricky to define a schema here. It's a bit of a mess. There is no regularity. There is an array with E that has integers, a nested array. Then you have an array associated with B that has all kinds of values. This would be tricky to define a schema. You could, but it would be very lax as a schema. This document here, however, I would like you to develop the intuition that here we can do something about it. Why? Because look at the array C, for example. Look at the structure. We have a key foo that's associated with a string, bar1, bar2, bar3. We have bar that is an array of integers. Here you see some pattern and some structure. Who sees that there is structure in there? So I'll show you now how we define schemas that check for this structure, that ensure that if you have millions or billions of documents like that, you can make sure that all of these millions and billions of documents follow exactly the expected structure. In order to do that, I need to spend some time talking to you about types, the type system, because we are going to use types, strings, integers, and so on. Who already knows what a type is? If you programmed a little bit, you might already have some exposure. Who knows what a type is? Some of you, but not all of you. Okay. So the type is basically some constraints that you have on a value. For example, you might want a specific type to be a number. Maybe you want it to be an integer. So integer is a type of value. Another example is text. It's actually called a string by computer scientists. So a string, text, is also another kind of type, right? And we are going to cover that. Dates are another kind of type. Objects, that these are also values. The objects, these are also, you can define a type that is object and so on. So generally, all type systems, and here this is super general. What I'm going to tell you now is not just JSON or XML, or it's a lot. It's Java, it's Python, it's C++, it's almost any languages you can imagine work in that way. So I'm going to give you a very generic introduction to types, then we'll come to the schemas. Almost everywhere, and that's good news for you because they all look alike, the type systems on the high level. Almost every type system makes a distinction between atomic types and structured types. They might call them complex types, there's different names for that, but there is a difference. So I'm going to explain to you what is an atomic type and what is a structured type, of course. You probably already guessed, right? In JSON, string, number, Boolean, null, these are atomic types, and object array, these are structured types. But you also have that in Java. In Java, a class is a structured type, right? But an int or a Boolean would be an atomic type. In Python also, you have the notion of lists, dict, and so on. Who knows that in Python? Some of you might know Python, right? So this, dict, list, and so on, these are all structured types. Then we consider int, float, and so on. These are all atomic types. Okay, so whatever language you learn, there will be this distinction, almost guaranteed. So let's go through the atomic types. So the atomic types, if you look at the tree that I showed you earlier with JSON and XML, but you can also do the same with Java or Python. Technically, you could also draw trees. I'm going to explore atomic types. These are the ones that are the leaves in the tree. They don't have any children. Objects and arrays, they have children. They have members in an array. There's value associated with key, values associated with keys in objects. But the atomic types, they don't have any children, the atomic values. All right, so let's start with the string. Strings is just a fancy name that the computer scientists have for text. It's just a sequence of characters, right? So these are all examples here, including for those who like fancy literature, one of the most famous starts of a novel. So these are basically strings. I actually don't have much to say about that. This is just text, right? So for those of you who didn't know, that string is actually what this is. It's called a string of characters. All right. Then we have numbers, but we have several kinds of them. So I'm going to, there's basically 3 or 4 categories of numbers. But again, for those of you who already have used, let's say Java, C++, I'm not saying Python. Python is a bit special. Who already experienced Java, C++, these languages, who heard about short, byte, int, long? You've heard about these, right? So these are actually, this is very old. This is from the very early days of computers, even when we didn't have a lot of technology available yet. You know that the numbers in computers, we store them with zeros and ones, right? And in base 2, basically, just like we have in base 10 when we do it in our everyday life, but computers, it's in base 2. So there's only zeros and ones. And what happens is that you can constrain the interval of numbers you allow by restricting the number of bits that they use to be written. And this is what it means, short, byte, int, long, and so on. So a short is basically an integer that needs 8 bits. So it's going to be between 0 and 255, if you look at positive numbers, right? 2 to the power of 8, that's 256. But if you start with 0, that's 0 to 255. Then you have on 16 bits, then that's the square of that. So that's roughly 65,536, I think. You might get that wrong now under the demo effect. But anyway, 32 bits, I think, goes all the way to 4 billion, I think. and 64 bits goes to 16 quintillions. So that's actually very, very large. And if you think that's too much, then actually, who remembers on YouTube Gangnam Style? Remember these times? That's the first video that actually broke the YouTube counter. Can you believe it? They were using ints. That only goes to 4 billion. That was the first video ever that actually went back to the negative at some point. So they had to actually change the system to using longs just because of that video, and now it has become almost normal. But just to show you that we actually do need 64 bits from time to time. All right, so this is the easy part because these are just integers. You count from 0 to some number. You also have a way to have negative numbers if you prefer as well. Okay. Second, do we have a question on Zoom, or was it only the confirmation that somebody could hear me? Ah, okay, awesome, because I see this one here. Okay, so the next thing you can do with numbers is decimal numbers with a decimal point in the middle. So the first way you can do that is with a fixed point decimal, meaning that you say how many digits you're going to have left and right of the comma. So the number of digits, and here this is base 10, in base 10. So the number of digits on the right is called the scale, right? And the number of digits in total is called the precision. And if you do the subtraction of the two, then you get those on the left, right? This is called fixed point decimals, right? This is especially useful in accounting, because in accounting, for example, if you're a shop, then you probably want a scale of 2 for the rappen, the cents, right? So this is just an example of usage of fixed point decimals. We also have, and this is actually thanks to the evolving technology, because it's a luxury that we did not have actually 20 or 30 years ago, at least not only in mathematical software, but now it's becoming common, that we have arbitrary precision and scale. You can basically store absolutely any decimal number, no matter how many digits. Of course, not heptillions of them, because that's obviously going to break, but in theory, it's completely unlimited, right? You can store any decimal number. In XML and JSON, this is supported. You can absolutely have any arbitrary precision and scale for your numbers. Then there are the so-called floating point decimals. What is that? This is basically a way to store very efficiently some decimal numbers and to compute efficiently, meaning that the CPUs that are in the machine, so the CPU cores, they are very good at adding and multiplying decimal numbers if they are expressed in that format. And this is actually a standard that's called IEEE 754. I have no idea why I know that by heart, but it's IEEE 754. And that's a standard that tells you exactly how you encode these numbers on 32 bits or on 64 bits. If you encode it on 32 bits, this is called a float, typically. And if you encode it on 64 bits, this is called the double. At least this is what is done in Java, C++, and many languages, except Python. In Python, they had the idea of calling floats the double precision one. But once you know it, this is no problem at all. All right. So what is the constraint here? Because obviously there's a constraint. If you have a limited number of bits, you cannot go to infinity. So the constraint is that if you are on 32 bits, you can only have 7 digits of precisions. Right? That's it. But it can be with any power of 10. So that can be 7 digits and then 100 zeros. That's fine. That's the number with the 7 digits times 10 to the power of 100. And that you can do because you store the power of 10 separately, right? So you first store on the orange zone the 7 digits, and on the blue zone, on the orange zone, the power of 10, and then in the blue zone, you store the digits. And the gray zone has the sign, negative, positive. Double precision, it's just that you can have 15 digits of precision. But again, it's floating point, so you can have 15 digits, but maybe 200 digits after the comma, right? As long as you have no more than 15 that are non-zero in a row. And then you can store it with double precision. And you see with double precision, you can even have a power of 10 between 300 and minus 300 and 300. So that's a pretty large interval. By the way, the standard is flexible enough that you also have a version with powers of 2 for those who prefer powers of 2. So the 2 actually coexist. You don't need to understand how this is mapped, the layout. This is for computer scientists. We actually teach these things, but you really don't need to worry about that. All you need to worry about is knowing that there is a precision of 7 or 15 digits, depending which version you use. All right, So this is it for the numbers. Next, the Booleans. The Booleans, that's going to be very quick because there's only two of them. There is true and there is false, right? So it's really just one bit, one for true, 0 for false. But you also have plenty of ways to see it in syntax, especially in SQL. You can see why, yes, on, off, no, and. So there's many, many ways, right? If you know C++, then you probably know that you can also put a 0 or a 1 for true and false, and that will just work as well. Okay, well, this is it. This is the Booleans. There's only two. If you followed the Information Systems for Engineers lecture, you might remember that in SQL, in relational databases, there is a third value that is undetermined, right? It's null or unknown, right? But here, there is only two values, true and false. Then we have dates and times. So there are several of them. First, you have dates. That is a year, a month, and a day. The most popular one is the Gregorian calendar, but as you might know, there's plenty of other calendars, and some systems might actually support other kinds of calendars. But this is the most popular one. Right, so there's nothing much to say about it, right? It's just a date. Then we have times, which is the number of hours, minutes, and seconds within a day, typically with going all the way to microseconds. It's quite common, right? So you can have 6 digits after the period for seconds. Then you have timestamps. So the timestamps gives you everything. You have the year, the month, the day, the hours, the minutes, and the seconds. Right? It's a point in time. Something to be careful about is that you also have time zones. So some of the types will allow specifying a time zone, saying, okay, this is in Zurich. You also have types that don't specify the time zone. It's just some timestamp in an unspecified time zone, right? But that's basically it. So you have types, you have time, and you have timestamps. Then you have intervals. What is an interval? Well, for example, well, here are the examples. That's much easier to show you the examples. So 2 years is an interval. 2 years and 4 months is an interval. 4 months is an interval. 3 days. 4 days and 3 hours, 4 days, 3 hours and 2 minutes, 3 hours or 14 minutes or 14 minutes and 15 seconds. These are intervals. But you might have noticed this scary wall in the middle, because I draw here some scary bar there that we don't cross, right? Well, we can cross it technically, but we shouldn't cross it. Does anybody know why? What I mean with that is if I tell you 2 months and 3 days, for example, that's the duration, 2 months and 3 days. Exactly, it's not exact. Did you also want to say this? Awesome. Yes, indeed, because in a month, you might have 28, 29, 30, or 31 days, right? Because of the ways the calendars are built. So this is why you should avoid crossing that line, right? But if you say years and months, that's unambiguous. There's always 12 months in a year. And the same on the other side, there's always 24 hours in a day. Well, at least GMT. There is always 60 minutes in an hour and 60 seconds in a minute, right? So yeah, that's the only thing is between months and days to be cautious about. Then we have the binary type. Well, that's basically whenever you want to store pictures, videos for your streaming platform and so on. So it's just a bunch of zeros and ones, but that's actually anything. It's, you know, anything can be encoded with zeros and ones on a computer, right? So if you don't want to specify, just a binary format and that's it. Then you can store whatever you want. All right. And finally, null. Well, technically that was the third value for Booleans, but technically it's allowed anywhere. Again, if you use Java, C++, Python, null is something you've already seen plenty of times. Who is familiar with nulls? Okay, we also saw them in JSON, by the way. And they also exist in XML, even though I didn't show you, but there's also a way to have a null value in XML. Okay, I just didn't want to annoy you with that. Okay, so these are the types. So atomic types, more precisely. So these are values that I've showed you. But I showed you on the logical level. When I say, for example, April 18th, 2023, that's a logical concept. But in JSON or XML, this is text. So we need to write it as text in any case, right? And we need to do it for strings, it's easy. For the strings, it's easy. But for numbers, Boolean, dates, and times, more complicated than it seems to actually have it as text. And this is why we have a distinction for atomic types between the value space and the lexical space. Right? The lexical space for a given type is all the possible textual representations of values. I insist on textual representation of value. 4 is the digit 4 is a representation of the number 4, right? Of the 4-ness, if you want. It's basically, so if you want to go into axiomatics or mathematics, 4 as the number can be defined on an equivalence class of sets. These are all the sets that have 4 elements. That's the mathematical abstraction of 4. But you need to represent it as text, which you can do in base 10 with 4. You can also do it with plus 4 is 0, which means 4 times 10 to the power of 0, if you want. That's the scientific notation. You can do it in binary form. In some languages, you do that with 1 and 0s followed by a b, right? So you can do that. You have all of these representation. What you need to understand is that in the end, when you parse the document, you really want to query it based on the actual value and not care anymore about how it was represented in the syntax. So there is this mapping back and forth between lexical space and value space. For whom is that clear? All right, so for numbers, it's natural. For dates, it's actually a huge mess because there are standards, of course, but everybody feels like they should reinvent something whenever they design a new language. But anyway, in XML and JSON, the common way to store dates is with dashes. You have 4 digits for the year, and then a dash, and then 2 digits for the month, and then a dash, and 4 digits, 2 digits for the month and 2 digits for the day, right? So if you have, that's text on the right, 2017-08-01, that's actual text, that's in the lexical space. In the value space, logically, this is the 217 August 1st ness that is actually meant here. Right? That's the logical concept of August 1st, 2017. For whom is that clear? All right, so this is the convention, but of course, you will see, especially if you use JavaScript, you will see that there's plenty of other ways to represent dates, including writing in English 2017, August 1st, and so on. Some people actually do that. Okay, then we have, for the timestamps, where we have the whole thing, the year, the month, the day, the time, and so on, what is done in XML, and that's actually a standard. I think it's ISO 8601. Again, I have no idea why I know that, but this is the name of the standard. And what you have is just the same for dates with digits with dashes. Then you have a big T, an uppercase T, and then you have the hours on 2 digits, colon, the minutes on 2 digits, colon, the seconds on 2 digits. You could also have a decimal period and further digits for all the way to microseconds. And Z is just the UTC or GMT time zone. All right. I should have written GMT. Who knows the difference between UTC and GMT? Yeah, no, maybe I'll give you, but as a piece of fun fact, you know, that's not part of the lecture. So UTC is technically based on the duration of a second when you measure exactly the elapse of time in seconds, right? Based on, I think, vibration of, I don't think it's quartz, it's probably something else, but that's the idea, right? You define the duration of a second, and that's how you measure time, and you let time elapse. GMT is based on the rotation of the Earth, right? So the rotation of the Earth takes 24 hours, and so you divide the days into 24 hours, then divided in 60 minutes, and so on. As you might know, the two do not coincide, because actually, the rotation of the Earth is slowing down. Keeps slowing down, slowing down, slowing down. So if you go millions of years earlier, the Earth was rotating faster, and in the future, it's going to rotate slower. So as a consequence, the two do not exactly coincide. And in fact, it is not continuous. Sometimes the Earth accelerates again, slows down again, and so on. And that's the reason why you might see in the newspaper every year some big announcements that on December 31st, there is this leap second, right? So you heard about the leap second, right? Who heard of this? Okay, so that's the difference between UTC and GMT. Basically, the leap second means that UTC is off compared to the rotation of the Earth, and we change UTC back to coincide with GMT to not lose our sanity, right? But there are people who actually suggest that we should no longer synchronize them. All right, but anyway, parenthesis closed. Z is basically just to say GMT or UTC, and then you have also the possibility to define 2 hours for Zurich, -7 for Pacific time, and so on and so on. All right. And durations, it seems complex, but it's really not. Look at the right, 1Y, that's 1 year, 2M, that's 2 months. The T, that's the same T we had here. To this, that's the wall between days and hours. T, and then 3H or 3 hours. Note that what I did here is for the purpose of illustration, but you shouldn't do this because 2 months and 3 hours is ambiguous, right? But I just wanted to show you that the general syntax, but typically you either have something on the right of the T or on the left of the T, but not both at the same time. All right. Then if you programmed with Java and Python, you might have heard of subtypes. For example, you might know that integers, that's a subtype of decimals, because an integer is a particular kind of decimal number that has no digit after the decimal period, right? But it is also a decimal number. So if the value spaces, so the spaces of all values for a specific type is included in another type's value space, then we say that the first is a subtype of the other one, okay? And when you define in Java or Python classes and subclasses and so on, then typically you define subtypes. Okay, but I'm not saying so much more than that. All right. So atomic types, for whom is that clear what an atomic type is? Okay, what I showed you is universal. This is more or less everywhere you have these types. They might not be called in the same way everywhere, but this is how it works. Okay, and finally, that's the structured types. We also have maps and lists. In JSON, the maps would be JSON objects. This would be JSON arrays. You also have maps in XML if you look at a set of XML attributes in the same element that can be seen as a map. An XML element can be seen as a list of its children as well. And data frame, I'll come back to that. Data frame structs and arrays, I'll come back to that. But basically, the two structures you find almost everywhere are maps and lists that you find almost everywhere. So think objects and arrays. This is universal. Something else that you find in not all, but some languages, because some languages do not support that, but in the languages that support sequences, you can specify that you have 0 or more with a star. That's how computer scientists like to write that. The question mark means you have 0 or 1 value, and the plus means you have 1 or more values, right? But we'll come back to that when we study query languages later. Another way you might find is repeated for 0 or more, optional for 0 or 1, required for exactly 1, and so on. This is also kind of universal. You might have deviations. Now, by popular request, and that was actually your colleagues a few years ago who asked me that, because I told them, okay, we have a universal system, but it's a universal system that works pretty much like Schweizerdeutsch. So it means we have Baseldeutsch, Berndeutsch, Ostschweizerdeutsch, and so on and so on. And that means concretely that even though what I told you is universal, this way of classifying types and so on, even in spite of that, the names that they are called and the exact specifications might vary. So whatever you learn as a new technology will be very easy, but you will still need to do an extra effort and look at the documentation to see how the types are called and how they are specified. This is an attempt to show you the correspondence between all of these technologies. So there is Python on the right, there is PostgreSQL, that's a relational database, Spark SQL, we'll look at it in a few weeks, XML schema and JSONic, that's the same ones. So this is easy. And then you have JSON schema that might be a bit more complex. But basically, this is just for you as a reference so that you can see the correspondence between the types. But I hope that with this, you see that this is really universal. We might not call things the same way in every village of Switzerland, but we all understand each other. All right? Okay. This is for the types. Hopefully a 101 that is completely neutral, not specific to JSON and XML, but in particular applicable to JSON and XML. So now that we have the types, I'm going to show you how to use them to validate data, to validate documents. So let's start with JSON that was specifically designed for teaching. It's meant to be simple. So on all of the strings that are now going to appear in here, I'm going to put on the top part, so I'm splitting it into my screen. On the top, you have a JSON document that's called an instance. It's a JSON document that is well-formed. And at the bottom of my screen, I have a schema. That schema tells me what constraints I want to impose on the document. But you might notice one thing, is that the schema is actually also looking like JSON, doesn't it? The schema just looks like JSON as well, right? It's the same for XML schema. In fact, XML schema also looks like XML. It's just that it's very convenient to do it because it looks a bit like the same. But you will see it will very quickly become clear. So look at the top, last Einstein. Imagine that what I want to validate is that if my document has a key, if my object has a key called last, I want whatever value is associated with it on the right to be a string, quote it. How do I do this? Well, I write last string, that's it. And string comes from here, from that menu. Okay, so last string, and we say now that the document on the top, last Einstein, is valid against the schema at the bottom. This is called the schema. Here's another one. We now have last Einstein, first Albert, and I specify with my schema at the bottom that last must be associated with a string value, and first must be associated with a string value, right? Next, you should know that this is also allowing to be absent. So if I say first string, I'm saying if it's there, it must be a string. If it's not there, that's fine too, right? So the document on the top is also valid against the schema at the bottom. But if it was something else than a string, then it would not be valid. Okay. To require fields, because I might want, as part of my schema, to say, I don't want optional. I want my fields to be there. I want my keys to be there. So if I really, really want last and first to appear, I just put that exclamation mark on the left. And that says last must be here, first must be here, and they must both be strings. Who is following? Okay. So you see the two look alike, right? That's exactly the pedagogical goal of JSON, that the document looks a lot like the schema. Then I can use integers. For example, I can say last is a string and age is an integer, and then the document on top, you see age 142, that's an integer, so it's technically fine. It would also be valid with quotes because all it checks is for the lexical space. Remember the lexical space I told you about? It is a 1, a 4, and a 2. That's fine. You can pass that as an integer, so it's accepted. Okay. Booleans, that's another data type from the menu. So here, physics is true. That's valid because physicist expects a Boolean. And what types do we have? Well, it's a whole menu. We have null as well. Null is also a type that has only one value that is null. And I put a menu for you that's almost a complete list of everything you can pick from, right? And that shouldn't surprise you because that basically corresponds to what I told you about types earlier. It's just the fancy names for that you have for the types, okay? And this here is just also sorry, what I showed you here is also the same. The yellow column on JSONic and XML schema, that's basically the same as what I'm showing you here, except that this is more complete. Maybe here you might have more of them. Okay, so some of them, of course, are very common. Some others are not so common, but it's a good idea to at least make sure that you understand what they actually mean. Okay, if you have any questions, then come to me. All right, or to your next TAs. Does the order matter? No, the order doesn't matter. So a question on the chat. As I told you in JSON, an object is a map. In a map, the order doesn't matter. So you can have, in that case, last Einstein location null, or you can have location null last Einstein, and that's just fine, right? Does it answer a question? It's a very good question. Yeah, all right. But in an array, the order actually makes a difference. Okay, now how do I say that I don't actually care about the value? Well, you can just use item. If you just write location item, that means anything. Item is just the type that contains anything, any value. So here it's an array with Switzerland and US, but it could actually be anything. Okay. Then how do I ask for an array? Well, I can just use exactly the same syntax with the square brackets and item inside. Item means I can have anything in my array, but I want an array. And you see here I have an array with one full null true. It's a mess, but it's still an array. And the document on top is valid against the schema at the bottom. What if I don't want a mess? If I want an array of integers, an array of strings, an array of dates, whatever, then I can do that. Absolutely, I just need to put these square brackets around integer, whatever type I want. And now I'm requesting that this is an array of integers. I can also have an array of objects, and I can even require that all of the objects have also a specific structure. So here, this is an array of objects, and all of these objects, if they have a key foo, that must be a Boolean. And you see, this is the case on the top. We have an array of 2 objects, and each one of these objects has foo associated with a Boolean. For whom is that clear? Who finds it intuitive? right? It really looks alike, right? This is exactly the goal pedagogically. Okay, by default, extra fields are forbidden. So if you if you have a document that not only has last and first, but middle, for example, that's not valid. You don't allow that. Okay? But you can opt in to allow extra fields. However, this is a power user thing. So if you want to have this feature, you need to switch to a more complex syntax of JSON, that is the verbose syntax. Sounds very scary, because this one is the simple syntax. As you can see, it's relatively simple. But there is a verbose syntax, very, very verbose. But this comes with all the bells and whistles of plenty of extra features. I'm not asking you to actually master that verbose syntax. That's just to show you that it exists. And if you use the verbose syntax, so in that case, we say we have an object, the base type is object, the content is must have named type, name type, and so on, right? So the name of the key must be last, the type must be a string, and then we have the key first must be associated with a string. It's very verbose, right? But with this verbose syntax, I have more power because now I can add this closed false, and that basically means that I'm not allowing for anything extra. If I do this, then it means, so closed true would be you're not allowing, closed false would be you're allowing for extra fields. Closing means you're forbidding extra fields. So if I say closed false, that allow for that year 1905, it's okay, because now I allow extra properties. Okay. You don't actually need to remember that. I just want to show you it exists. The one thing you need to remember is that with the simple syntax here, we do not allow extra keys that are not specified in the schema. Okay. So you can see in a schema language, we can have a lot of features. We can restrict values to have a specific types. I showed you how. We can implicitly cast. So if I have a string that turns out to be digits, I can cast it to an integer. I can require a value to be present. I can allow for extra keys or not allow for extra keys. I can also have default values. If a key is missing, then I can automatically populate it with some default value. And I can even have primary keys. For example, if I have an array of objects, then I can say that one of the keys cannot be repeated. I'm not, for example, the social security number, if you have an array of persons, then I can restrict that the social security number cannot repeat. Okay, that's just an example, a couple of examples of what you can do. Now, this is a concrete example of the great language game, which we will actually use in the exercises on the top. And the schema that you see is extremely simple to describe at the bottom, right? String, 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 array of strings. Hex binary is just a binary format that uses base 16. As you can see, base 16, 48F9C9, that's 0 to 9 and A to F, that's called base 16. And then the date with what I showed you with the dashes and so on, right? So who understands that the schema here, the document on the top is valid against the schema at the bottom, right? Okay, so this is how it works. And now if you come back to this document right here that I showed you earlier saying this has a pattern, well, here's the schema. Should be intuitive, right? A is an integer, B is a Boolean, C is an array of objects, foo string bar long, and I have foo is required because of the exclamation mark, bar is not required. This document is valid against that schema. But now we can use that same schema on millions, billions of documents and check that they are valid against the schema. Who now has an intuition of what a schema is and what we can do with the schema? Validation. Awesome. Okay. Now you have this page that you can go to if you want. You can play, you can put a JSON document on the left, you can put a schema on the right, or the opposite, schema on the left and the JSON document on the right. And then you can click the button and it will tell you if it's valid or not, right? So if you want later, you can play around with this page for you as a convenience. All right. Well, basically, I would technically be done with the schema validation, but now I just want to show you that there's other technologies out there, but I'm going to be very quick on them because I want you to understand that this is really the same. It's just a different way of expressing things, but it does the same thing. So now I'm going to show you JSON schema. That is a popular way of doing things. The one thing I want you to see is that it does the same thing as JSON. Might not use the same way of expressing it, but it does the same thing. So I'm going to be quicker and you will have exercises to train on that. But look, we're going to do the same thing. Do not be scared. It's not as simple or compact as JSON, but it does the same thing. So the document on the top is valid against the schema at the bottom. It's a JSON schema. It's no longer JSON. And you see I have a type, it's an object. And the properties, there is last that has the type string. And last is a string, so it's valid. Next, I can have several properties. Property is how JSON schema calls the keys, right? You might have key, fields, property. There's plenty of ways to call them. But anyway, properties, we have last that is a string, first that is a string, so it's valid. It's also optional, just like in JSON. If you don't have one of the properties, one of the keys, that's fine, that's valid. You can also require fields, but here you don't do it with exclamation mark. In JSON schema, you do it by listing them in required. You see, required is a list of the keys that are required. Last and first are required, okay? But it does the same thing as the exclamation mark in JSON. Extra fields, here it's different. By default, extra fields are fine. They are fine. So this document on the top is valid against the one at the bottom. This is totally fine, but you can forbid them. It's the opposite of JSON. In JSON, by default, it's forbidden and you can allow them with the verbose syntax. JSON schema is the opposite. By default, it's allowed, and you can forbid them with additional properties, false. Let me get rid of the bar at the bottom. Just need to do this, and there it's gone. Additional properties, false. This is how you disallow extra keys. Okay, now you have numbers like this. However, a word of warning, in JSON schema, you don't have that huge menu that I showed you. It's a bit less convenient. You have a more restricted list of the types that you can have, and it takes more efforts to actually constrain them a little bit more. So you just need to be aware of that. There is string, there is number, there are a few others, but not so many of them. Boolean is also there. You basically have all the JSON ones, right? String, number, Boolean, null, object array. Right, so this is Boolean. This is null. If you want to allow for any value, don't ask me why, that's the design. Just put a true in there. Location true means any value is allowed. Location false means I don't want to see a key called location. Forbidden. If you have a key called location, then that's not valid, right? So this is what true and false do in the schema. And as I told you, the type system is a bit simpler. What we can do, we can also do it in JSON. I just didn't want to overcomplicate things, but just so you see, I can even say that I want latitude and longitudes to be numbers, but I want them to be restricted. If I have a latitude on Earth, that's between -90 the South Pole and 90 the North Pole, and -180 for all the way to the west, Alaska, and maximum 180, technically also Alaska, and that's it. But you restrict it in this way. You can also do it with the verbose syntax of JSON. I just didn't show you how. Okay. I can also say that my type is array. That's also fine. And I can also further constrain the members of the array to all be integers. You can see it's just more complex than in JSON, the syntax, but it does the same thing as JSON for specifying arrays of integers. Okay, that's it. So that was quick, the overview of JSON schema. But again, what do I want you to understand? JSON and JSON schema do the same thing. This is what I want you to understand. JSON is the way pedagogically that I used to teach because it's simpler to understand, but you will see JSON schema in the exercises does the same thing, just with a different approach. After the break, because now you deserve the break, I'm going to show you XML schema. It's also going to be short. I actually shortened it even compared to previous editions of the lecture, because what do I want to show you with XML schema? I want to show you that it's the same thing really as JSON and JSON schema, just on XML. Right? This is the one thing I want to show you. So I'm not going to tell you so much about XML schema. You will have exercises if you want, but really, please look at this from a distance. What is important here is to understand what a schema is, that you can validate data to check that it fulfills specific constraints, especially if you have millions or billions of records. And I want to show you that there's plenty of other schema technologies out there, probably 10 or 20. If you know one, you know all schema technologies. It will be very easy for you to learn any of them. Right? So let's take 15 minutes of break. It's 9, so let's come back at 15 past 9. I will show you XML schema. I'll talk to you about data frames, which you will see is just a nice visual representation of valid JSON. It's kind of fun. And then we'll start with MapReduce. All right, so I see you in 15 minutes. Thank you.